senior student from National Taiwan University. And today I'm going to present my research on automatic crop identification for agricultural survey using farmland images and deep learning. And my advisor is Dr. Yunfu. First, let me introduce what an agricultural survey is. And it is the process of understanding which crops are grown in specific areas, and collecting the information on the crop condition and the cultivation area. And this information will be documented with images and tables. And the information can be an important basis for the government agencies in formulating agricultural policies. And in order to maintain the stability of market prices, distribute agricultural subsidies, and formulate industrial development strategies. And let me talk about the current method used in agricultural survey in Taiwan. Many other countries use satellite image for the agricultural survey, but in Taiwan, farming often involves many different crops grown in small scattered plot lands. So the resolution of satellite image may be too low to identify the crop. So in order to collect images with higher resolution, what Taiwanese government do is to send people, who we call them enumerators, to the field and do the agricultural survey manually. And the enumerators will use a mobile app developed by the Food and Agricultural Agencies and to take the photos of the crops. And then they will record the cultivation area by geographic information system and the crop types manually. Moreover, it is important to know whether an area is used for farming. So it is also necessary to record the non-crop areas. However, the current method exists problems. And the main problem is that there is a shortage of experts capable of accurately identifying the crop types. So most of the enumerators are part-time and have lacked professional experience in crop identification. And this leads to misidentification and diminish the quality of the survey. So in order to enhance the quality of the survey, the objective of this research is to develop a model that can automatically identify 53 most common crops in Taiwan, which we call them target crops. And however, anomaly input may cause problems for the identification model. And if our images are not any of the target crops, we expect our model not to incorrectly classify them. Instead, it should inform us that the images do not belong to any types of the crops. Therefore, our human resources only needs to focus on those images that fall outside of the target categories, which can reduce labor costs. And the target crops in the dataset in this research includes 53 most common crops in Taiwan, and has a total amount of over 165 images, which accounts for 2/3 of all crop images. The target crop images were defined as in-distribution images, or ID images. And the images that are not of the target crop were defined as out of distribution, or OD images. And non-target crop images, which are also crops but not belong to any of the target crops, or non-crop images, which can be building or low quality images, are both considered the OOD images. So this is the pipeline of the crop identification for now. And in order to achieve our goals of this research, the manual part will be replaced by 3 components: feature extractor, OOD sample detector, and the crop type classifier. And we will begin with the feature extractor. The purpose of the feature extractor is to extract a feature from the input crop images to the feature space, and will further become the input of the OOD sample detector and the crop type classifier. The encoder of the vision transformer was chosen to be the feature extractor. And the input images are RGB and was resized to 384 by 384 pixels. And the output of the second-less layer was used to represent the feature vector of the images. And the encoder was pre-trained on the ImageNet21K public dataset. And all the layers were fine-tuned on the crop dataset by softmax loss. After the feature were extracted, then will be the OD sample detector. And the OD sample detector determines whether the input image is in distribution or out of distribution. And if the input image is detected as out of distribution, it will require further manual identification by experts. Otherwise, it will become the input of the crop type classifier to classify which crop it is. And the main idea of the OD sample detector is to calculate the distance in the feature space between input feature and the distribution of each class. And if the input feature vector is too far from the distribution of each class, it will be considered out of distribution sample. So first, in the training process, we have to use the features extracted by the target training images and to find the distribution and calculate the centroid of each class in the feature space. And after the centroid of each class was determined, if there is an input image, we want to know whether it is in distribution or out of distribution. We will similarly extract its feature into the feature space, like the V1 in the slide. Then the Mahalanobis distance between V1 and the centroid of each class in the feature space will be calculated. And the distances will be vectorized into a 53 by 1 vector. And the vector will soon become the input of a support vector machine classifier to determine whether it is in distribution or out of distribution. And for the result of the OD sample detector, the confusion matrix and the receiver operating characteristic, or ROC curve, were shown on the slides. And the overall accuracy reached over 90% of them, and achieved an AU-ROC of 0.98. And this result indicates that this model can effectively reduce the workload of laborers in real-world applications. And according to the 2023 statistics from the Ministry of Agriculture, and based on the ratio of ID and OD images, the model can reduce the current workload by about 65%. And with only 3% of images will be misclassified as an input for the crop type classifier. And next, I would like to discuss the interpretability of the OD sample detector. I use non-target crops and non-cropped images separately as the testing data for the OD sample detector. And the non-target crops are more similar to the target crops with a closer distance in the feature space, and making the detector more likely to misclassify between them. On the contrary, non-crops images are less similar to the target crops, with a greater distance in the feature space, and making the detector easier to distinguish between them. So, based on the comparison between these two, I believe that the difference in the result provides a reasonable explanation for why we should use an support vector machine classifier using distances to the centroid of each classes as input. And finally will be the crop type classifier. And the purpose of the crop type classifier is to accurately distinguish between the 53 types of crops. The crop type classifier was composed of multi-layer perceptron, or MLP, and the extracted features of the filter dataset by the OD sample detector will become the input of the crop type classifier, and then output the class of the crop type. And the crop type classifier was trained by cross-entropy loss and SGD optimizer. For the result of the crop type classifier, the overall accuracy achieved over 93%. And most of the classes can be correctly classified, but a few are more prone to misclassification. And we will take a closer look to the metric to analyze their errors. And so the main issue leading to the misclassification is the similarity between classes. From the confusion matrix on the slide, we can see that the model easily confused these four crops: broccoli, cauliflower, cabbage, and Chinese cabbage. And the reason they appear so similar is that is because that they belong to the same species in biotaxonomy. And the similar situation occurs in lychee and longan, betel nuts and coconut, and citrus and grapefruit. And the reason for their misclassification is also likely because they belong to the same family or genus. So in summary, the OD sample detector achieved an AUROC of 0.98, which could reduce 65% of current workload. And the crop type classifier achieved an overall accuracy of over 93%. And some classes were poorly classified because of the similarity between the classes. For my future work, I will discuss with the experts the situation of distinguishing similar crops and figure out how to deal with these classes in practical applications. And finally, I will deploy this system on a mobile app for practical use in Taiwanese agricultural survey. And sincerely thanks to Professor Liu and Professor Tsai from the Department of Agronomy for providing expertise on crops, and to the Dr. Liu from Ministry of Agriculture for providing farmland images. Thanks for listening.
Thank you. Okay, we have over 4 minutes for questions, discussions. Yes.
Thank you for your presentation. My name is Lucas. I'm from Korea National University, South Korea. It's interesting for me that you mentioned that your system can reduce the workload.
Yeah.
It's about 65%.
Yeah.
I'm curious how you measure the workload.
Oh.
How you can get that 65% reduced workload.
Oh, based on this chart, we can see the ratio of the ID images and OD images, and in the real world scenario. And the OD sample detector have a true positive rate of 0.92, and it times the ID samples the 67%, and to get the 65 and to add the 0.11 times the OD samples 32%. So it's like 62% of ID images and 3% of OD images. So the 3% of images will be misclassified.
Do you mean this is like the workload from the enumerator? You
Yes.
said that
The image the enumerator have to identify. Yeah.
Thank you.
Okay, any other questions? Yeah, so I have a question. Why sunflower is OOD or strawberries?
Because it is not so common in Taiwan crops, and also the training samples is efficient. So our crop type classifier cannot easily learn the features of these crops.
Oh, okay. So you don't have much of these crops, and it's also difficult to train.
Yeah.
That's why you place that in OOD.
Yes, and further needs manual identification.
Oh, okay. Okay, and then OOD detector had some error. Can you explain the main sources of error? for OOD detection? Main sources of error. Well, why you have error? I think you can go to that result section for OOD. Right there. You see.
Yes.
So what is the main sources of error?
Sources?
Yeah, misclassification. Why do you have misclassification here?
I'm not pretty sure about the reason why they cannot easily identify between them, but I think it is because there are some images taken by the emitter. They are backlit, or they have the quality is too low to extract the feature. So the distance, so the input features in the feature dimension can not be clearly classified.
Mm. Okay. Yeah. Thank you. Yeah, let's give you another round of applause. Okay, our next presenter is here.